It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbet's Physics. What is crappin'? Today we are going to talk about Einstein's theory of relativity. And in fact, we've learned this before, both at the beginning of the year when we talked about relative motion, and also during the middle of the year when we talked about space and time during Newton's laws of gravitation. In proper form, I'm wearing an Einstein t-shirt, and also my cat Leo decided to sit in and listen on this lesson. Say hi, Leo. So, why don't we first talk about what we learned before, which was relative motion. At the beginning of the year, we talked about a person that was sitting in a chair, and all they did was they threw a ball up in the air while they were just sitting in it, and we saw the ball travel up and downwards. The people observing the person sitting in the chair saw this image, and the person also sitting in the stationary chair saw the same thing. But then we set the person in the chair in motion, and when they threw the ball straight up in the air, the people observing the person moving saw this parabolic path. So while we were watching a person travel across the floor, the ball traveled in this parabolic path. However, the person that was sitting in the chair, when they threw the ball in the air and also traveled to the right, they saw the ball travel just up and down because both they and the ball were traveling to the right. So based on our position and motion, we saw two different perspectives, but in reality, both things happened. And that's the essence of Einstein's theory of special relativity. So Einstein came up with two postulates for special relativity. The first one says that all the laws of physics are the same in all inertial frames, which means the laws of physics apply for an object that's moving in a straight line at a constant speed unless acted upon by a non-zero net force. The second postulate said that the speed of light in a vacuum is constant. And let's look at that in more detail. Let's say that you're sitting in your car, or truck, delivery truck it looks like, and all of a sudden, let's just say it's nighttime and you decide to turn the lights on, your headlights on in your car. So when you turn your headlights on, the light from your headlights are going to travel at the speed of light, assuming it's in a vacuum, which is 3 times 10 to the 8th meters per second. Now, after you turn your lights on, let's now say that your car starts driving forward by you steering it. And let's say that you're moving forward at 10 meters per second. And the light from your headlights was traveling at c, the speed of light, which is 3 times 10 to the 8th meters per second. Now, if we take a step back really quick, let's say that somebody is sitting in your car and they throw something forwards at 5 meters per second. An observer on the outside, if they want to calculate the speed of the object that you threw forward as 5 meters per second, they would have to add up both the speed of the object and the car, so they would observe the object thrown inside the car to be 15 meters per second. But things are different with light. light travels at a constant speed no matter what object is moving with it. So if the car is moving at 10 meters per second and the speed of light is moving at 3 times 10 to the 8th meters per second, the net speed is not the addition of the car and the speed of light. So it's not the sum of these two. The speed of light is going to be constant at 3 times 10 to the 8th meters per second, even though the car is moving forwards with it. So that's an important postulate because it's going to affect how time and distance change based on the fact that the speed of light is constant. We're first going to talk about how time is affected by the fact that light travels at a constant speed, and then we'll talk about how distance is affected as a result or consequence of light traveling at a constant speed. Einstein worked as a patent clerk in Bern, Switzerland, and it so happens to be that he worked above a train station, so a lot of his analogies involve trains. The first one has to do with how we view time based on each person's perspective. So in this scenario, we have a stationary train. O stands for observer. So we have an observer inside the train. S stands for stationary. So outside the train, we have a stationary person. We're going to look at the scenario in which we have 2 bolts of lightning that strike bells at A and B at the same time. So these 2 bolts of lightning, A and B, are the same distance away from the center bolt. So it's going to strike A and B simultaneously. The stationary observer, because they are right in the middle, are going to hear bells A and B simultaneously. The person sitting in the stationary train, because they're not moving and they're also in the middle of A and B, are going to hear the bells A and B simultaneously. But when we put the train in motion, we have a whole different story, especially considering the fact that the motion of the train does not affect the speed of light. So, if the train is moving towards the right, the person outside of the train are not affected by the train moving. So the person on the outside of the train is going to hear bells A and B at the same time based on the lightning bolts hitting it simultaneously. However, the person moving inside the train, O sub t, since they are moving towards bell B or object B, they're going to hear bell B first, and then it's going to take some time, but very little time, for the sound to travel from bell A to the observer. So the person moving in the train hears a completely different story in which bell B goes off first, and then they hear bell A. Both of these scenarios are 100% correct. So O sub S is correct when they say they hear A and B at the same time. O sub T is correct when they say they hear B and then A. So there's a change in time based on the idea that the speed of light is constant, as well as the fact that the person in the train is moving towards bell B. So let's look at a similar situation to give us a better idea of what's happening to time. In this scenario, we still have a train that's moving to the right. There's somebody standing inside the train, O sub t, somebody standing outside the train, O sub s. This time, we're going to say that O sub t took a laser, and it's isolated inside this container with a mirror on the bottom and the top of the train. And what happens is we're just going to look at one photon from the laser, and when it hits the mirror on the top, it's going to cause it to bounce down, and when it hits the mirror on the bottom, it'll cause it to bounce upwards. So the photon from the laser is just going to bounce up and down, up and down. The person inside the train that's moving along it sees the laser bounce, in this case down then up, down then up, down then up. This is exactly the same as the scenario of the person that threw the ball upwards in class, and they just saw the ball go up then down. However, the person sitting on the outside is going to get a different perspective of what the photon does inside the train. The observer on the outside is going to see a similar parabolic path that we saw of a person throwing a ball up in the air and moving to the right at the same time. So now, as the photon bounces up, it also bounces up at an angle, and it also bounces down at an angle. As we could see from this picture, it's going to take a longer path to travel when compared to the person sitting, inside the train. Which means if it takes a longer path, then it's going to take a longer time for the clock to tick. So if it ticks every going up and down, the tick is going to be longer. So the tick-tock will take longer to go up and down because it's moving sideways. So from this person's perspective on the outside, O sub s, they see the time running slower for the person on the inside of the train. So we're seeing that time is slowing down, which means the time to tick-tock is getting lengthened because it takes a longer time for it to happen. And we call it time dilation, which is the slowing down of time based on the motion of an object. Now, the weird thing about relativity is that it goes both ways. The person that's sitting on the train, they could say that they feel like they are stationary, and O sub s, the person on the outside, is moving to the left. And in this case, the same exact thing happens. The observer on the train, they feel like they are stationary. They think that the person that's on the outside of the train is moving to the left, and then therefore their time is slowing down. So when we talk about whose time is slowing down, it's very important to look at from which perspective are we looking at, as well as from whose clock are we looking at. And when we get to the formula, we'll talk about that in more detail. Let's now look at what happens to the length or the distance between 2 points when an object is moving and one object is stationary. In this scenario right now, we have a stationary train with the observer inside the train and an observer outside the train that's also stationary, O sub s. Let's say that they are both holding a meter stick, so they both measure 1 meter from end to end. We'll now put the train in motion, and it's going to move to the right, and we want to see what happens to the length or the distance between 2 points for the observer on the train. So what do they observe? To analyze this, we're going to look at the person's perspective on the train. So for their perspective, it looks like they aren't moving, and that the person that's stationary, that's not moving, it looks like they are moving to the left. So let's redraw the picture where the person on the train is stationary from their perspective, and the observer is moving to the left. What that means is that the person on the train, their clock is ticking normally, just up and down. And when they observe the stationary person moving to the left, their clock is ticking slower. So it's going to take a longer tick-tock to go up and down. Now let's just take some numbers and see what happens. Let's say that the train or the stationary person is moving to the left at 500 meters per second. No matter whose perspective we're looking at, either one is traveling at 500 meters per second. Either the person is moving to the left or the train is moving to the right. And let's look at the clock of the person moving to the left. Let's just say that its time is 2 seconds. And we'll say that the distance the train travels, is 1,000 meters. So if we just use V equals d over t, we get 500 meters per second is equal to 1,000 meters over 2 seconds. That is what it looks like is happening to the person moving to the left on the person's perspective on the train, from the person's perspective on the train. But if we look at the person's time on the train, it's going to tick normally, which would appear to be faster compared to the person that's not on the train. To keep numbers simple, let's say it's ticking, that it takes 1 second to travel 1,000 meters. And then we know it's traveling at 500 meters per second. And the time, that should be an equal sign. The time on their clock reads 1 second. And to compensate for that faster time, we can see that the distance has to change, and it has to get smaller, in this case to 500 meters. So the person that's moving on the train, the distance they travel, or the length of an object that they're holding, is going to shrink or contract based on time dilation. Also based on the fact that the speed has to be the same from either person's perspective. So, when an object is moving, from the person's outside perspective, we can see that their time inside the train is going to slow down. So they see a longer time. The opposite holds true if we're looking at the person's perspective on the train. So time slows down. If we look at the length of an object, we see that the length is going to contract or get smaller for an object that is moving away from a stationary source or observer. So that's the first part of Einstein's special relativity, is for objects moving at a constant velocity. Now let's look at Einstein's happiest thought. And to do that, we're going to look at a biography on Albert Einstein. And Einstein's happiest thought, if I could find the page, occurred in 1907. Let's read you a couple of paragraphs. Einstein's road to the general theory of relativity began in November 1907, when he was struggling against a deadline to finish an article for a science yearbook explaining his special theory of relativity. Two limitations of that theory still bothered him. It applied only to uniform constant velocity motion. Things felt and behaved differently if your speed or directions were changing. And it did not incorporate Newton's theory of gravity. I was sitting in a chair in the patent office at Bern when all of a sudden a thought occurred to me, Einstein recalled. If a person falls freely, he will not feel his own weight. That realization, which startled him, launched him on an arduous 8-year effort to generalize his special theory of relativity and, quote, impelled me toward a theory of gravitation, end quote. Later, he would grandly call it the happiest thought in my life. So let's look at that in more details. To get an idea of what Einstein is talking about, we're going to look at a picture of somebody inside an enclosed elevator without any windows, so they can't see what's happening on the outside of the elevator. And Einstein said, if somebody is in an elevator and they're in free fall motion, they're going to feel weightlessness. So imagine if you're in an elevator and somebody cuts the cord, it's going to be in free fall, which means you're going to feel weightlessness. That means your normal force would be 0 newtons. But he said the same thing can occur if you're somewhere out in outer space and there's no gravitational field around you, you're also going to feel weightlessness. So these two ideas of either being free fall, we could say on Earth, or in a 0 gravitational field are the exact same thing. And this is what Einstein came up with as the equivalence principle, where these two scenarios, if you can't see what's happening on the outside, are exactly the same. Now the same rules also applies. Let's say that you are in an elevator on Earth at rest. You're going to weigh F of g, the force of gravity due to Earth. But if you're out in outer space and there isn't any gravity, if the elevator is accelerating upwards at, let's say, 1g, or the acceleration due to gravity, so it's accelerated at 9.81 meters per second squared, you are also going to feel the same weight in outer space. So if you're at rest on Earth, or if you're accelerating upwards in outer space at g, you're going to feel the exact same thing. So there's no difference of being in a gravitational field on Earth or accelerating upwards in outer space with a 0 gravitational field. These two scenarios are also the same. Which leads us to Einstein's thought experiments on relativity and how light behaves in gravitational fields. In this scenario, we have an observer inside an elevator, an observer that's stationary outside of the elevator, and we also have a flashlight that's turned on, suspended, we'll say, on the elevator. And what's going to happen is at some point we're going to cut the elevator. So it's going to be in free fall motion, falling downwards, while the flashlight, we'll say it's turned off the instant it's cut. So we just see one photon from the flashlight and watch its path as the elevator is falling down. The person traveling inside the elevator, because they are moving with the flashlight or moving with a beam of light, they're just going to see the beam travel in a straight horizontal line. Just like we would think of if they threw the object straight up in the air, they'd just watch it fall straight up and down as they were traveling to the right. Now the person in the elevator, because they are in free fall motion, they don't know if they are either in free fall motion or if they're experiencing 0 gravitational fields. Both of these situations are equivalent. However, the stationary observer on the outside, they see this curved path of the photon as the elevator is falling downwards. Now the person on the outside knows that this elevator is being pulled down by Earth due to gravity. So they have a gravitational field which means it's similar to either a person being at rest on Earth where there's weight, or they're accelerating upwards in space, making them feel weight. As a result of this, there's two reasons why we can have this curved path of the photon. The stationary observer says that there must be two reasons that are going to cause this curved path. One of which is the acceleration of the elevator. In this case, it's accelerating downwards. But acceleration is also the same as being in a strong gravitational field on Earth. So Einstein said that the other scenario, this strong gravitational field, must be the bending of space-time that causes the light to curve. Excuse me. Because as we know, light must travel in a straight line unless space itself is curved. Sorry, I need some water. That's some good water. So Einstein said that the force of gravity is not some sort of imaginary force, but it's the curvature of space itself. And that's a result of the equivalence principle between there could be two things that are happening, and if you don't know, they have to be exactly the same. This was observed in, I believe, 1917, the idea that space itself bends during a solar eclipse. So here we have Earth on the bottom of the screen, Moon in the middle, and then the Sun. And if space itself does indeed bend light, then we can say if we know that a star at this given time should be located behind the Sun, and if the light is being blocked by the solar eclipse, then we should be able to see where we observe that star. So as the light travels from the star, it's going to, in theory, curve around space due to the mass of the Sun. Eventually it's going to reach Earth, and then we observe light as it travels in a straight line. So when we observe the light, it's going to appear in this location right here. And Einstein said, well, we can use my theory of general relativity to calculate, where the star appears to be where it's observed versus where it actually is, and we could compare those differences through calculations, but also through measurements. And if the measurement agrees with the calculations, then Einstein's theory of space-time, that space itself bends, must be correct. And indeed, when this happened in 1917, the observed star matched where Einstein predicted it would be based on his theory of general relativity as well as space-time and the curvature of space. That's it for this video. Thank you for watching, and I'll see you next time.